Welcome back to my channel where we talk about biochemistry, and if you've watched any of my videos in the past, you know that my love is biochemistry. Pretty much everything on this channel is biochemistry. There's some other stuff on here as well. If I do things that are not explicitly biochemistry, there's usually some way to tie it to biochemistry in some way. I always try to do that. But here's an interesting topic that we're going to discuss in this video because it's quite a hot topic, and it has been for quite a while. It's the topic of two things. Number one, ozone, which we'll get to in a few minutes. And then we're going to talk about this type of molecule referred to as a chlorofluorocarbon, a very, very dangerous and noxious molecule from the atmosphere's point of view. We'll talk about that. This is a really hot topic because there certainly are a lot of people out there, particularly politicians, who like to deny this existence of any kind of climate change. I mean, you can try to manufacture the idea that there isn't any, but when you look at all the data suggests otherwise. So this is definitely a real thing, and what I'm going to do in this video is I'm actually going to show you the inorganic chemistry, and certainly some things from organic will still apply, of how this actually works on a molecular level. So one of the things I want to talk about is, I want to talk about first the setup of our planet. Okay, so first of all, I think we all have the general idea that if I'm looking at some cross-section of the Earth, I have this outer layer that's usually pretty thin. This is what we refer to as the crust, right? And if I go deep to the crust, I get into a region referred to as the mantle. And then if I go deep to that, then you start getting into the core regions of the planet. Well, that's good and all, but the ozone layer is beyond that. It's actually in the atmosphere. So when you start getting above the crust and you get out here, this is, of course, where the atmosphere is. And there are different layers of the atmosphere, and this is a picture that kind of shows how it works. You go just off the crust of the Earth, and by no means is the Earth spherical, very, very much an irregular shape. You get just above the Earth, and you go up about 18 kilometers. You're in something referred to as the troposphere. This is the deepest layer of the atmosphere, so we're growing more and more superficial. You go superficial to the troposphere, now you're in the stratosphere. And on the superficial part of the stratosphere, this is actually where the ozone layer is. So this ozone layer is sort of shaded in this magenta color, and it would extend all the way around the planet. Maybe not for long. But in any case, the ozone layer is on the superficial part of the stratosphere. And you can go above that. You can go to the mesosphere. You can go to the ionosphere. We're really not concerned about that. That's, as far as any humans are concerned, that's pretty much too high to go. Usually when airplanes fly, they're flying generally here in the stratosphere and troposphere, so we're not going up this high unless you're going in a rocket or something. But the ozone layer is here in the stratosphere, and I want to go over some properties of ozone very quickly. So you can see very quickly we're going to get into some of the inorganic stuff. Ozone is what we call a molecule that has resonance. Okay, so this is going back to some of your organic type of knowledge, although this is an inorganic compound because there's no carbon. So ozone has a property which we call resonance. Okay, and we're not going to go into the mechanism of how ozone actually forms. Suffice to say that it's been there for a while. Okay, I'll do the mechanistic steps in green. And understand, these are not actual mechanistic steps. These are just abstract ways for us to sort of understand where we can distribute electron density. Because notice, this particular atom of oxygen right here has the negative charge. The positive charge generally is always contained in the central oxygen, but notice over here the negative charge is over here. So what I can effectively show is, for example, this is not a technical mechanistic step because this is resonance, but you could kick this in here, form a pi bond, causing these pi electrons to come out onto this oxygen. And so you end up with this resonance structure. Well, so you can say that the negative charge isn't fully on this oxygen or this oxygen, but the positive charge really seems to be on that central oxygen. So what I can draw is something referred to as a resonance hybrid, where I say that each of these terminal oxygens possesses a partial negative, because you can, depending on the resonance structure, you can put negative charge on both those oxygens, and then I'll put a full positive on the central oxygen, because that one in general always has a positive charge. And also notice that on the central oxygen there is an orbital right here of electrons, a lone pair, so this is a lone pair, that's not actually part of the resonance system. Okay, so this lone pair is not in a resonance system. In fact, if you were to actually look at this molecule, so in other words, what I have is, let me just sort of draw the resonance hybrid like this. So here's the resonance hybrid, and I have these electrons right here in the lone pair. And then this has a partial negative, and a positive charge. Well, if I look at sort of the regions of electron density, and where I'm getting at is electron domains, well, number one, there is one electron domain right here. We'll call that electron domain 1. There's another one right here. We'll call this electron domain 2. And then the lone pair here, this is actually what we refer to as electron domain 3. And so if you're looking at the molecular geometry of this molecule, it's trigonal planar. It's trigonal planar. And the reason it's trigonal planar is because it has 3 electron domains. Now, what I can do is I can look at the electron domain geometry, because it turns out of these 3 electron domains, I have one lone pair and I have two bonding domains. And this particular type of electron domain geometry is called angular. And oftentimes a very common mistake students make is they want to call this bent. Well, it turns out that bent is only the case when you have tetrahedral geometry. So for example, if I had water, so let's draw a water molecule. So water molecule has these 2 bonds from oxygen to hydrogen, and then of course you have these 2 lone pairs right here. Well, in this case there's actually 4 electron domains. So here's electron domain 1, here's electron domain 2, and it's arbitrary how you define these, but this is electron domain 3, this is electron domain 4. Okay, so this one has 4 electron domains, and so therefore it has tetrahedral geometry. That's the molecular geometry, tetrahedral. If you're looking at electron domain geometry, it has 2 bonding domains and it has 2 lone pairs, so that makes this have bent structure. However, when you look at the angles, generally the one we're concerned about is the one between these hydrogen-oxygen bonds. This angle turns out to be approximately 104.5 degrees. That's an approximation, of course. When you look at this over here, this angle right here, theta, actually is closer to about 120 degrees because it has 3 electron domains. So overall it's trigonal planar, but the specific type of electron domain geometry is angular, okay, because you have 1 lone pair and 2 bonding domains. So hopefully that gives you a little bit of intuition behind ozone. And let's go back to the problem. The problem is that we have this ozone layer that surrounds the Earth. Okay, it's located in the stratosphere. But herein lies the problem. The problem is that humans produce all sorts of nasty molecules. Okay, one example of a nasty molecule is called a chlorofluorocarbon. Sometimes I reverse the C and the F. So it's a chlorofluorocarbon, or a CFC. And later in this video, we're going to look at the mechanism as to how it destroys the ozone. One thing I do want to mention is that humans do produce this type of molecule, and actually a generic chlorofluorocarbon is shown right here. Okay, that's a generic one. That's probably the simplest one that you can get. Okay, so I have this ozone layer. It's in a sort of a spherical arrangement in the superficial part of the stratosphere. How does that help us? Well, number one, it protects against heat from the sun. Okay, so number one, it protects against ultraviolet rays from the sun, and certainly the range of electromagnetic spectrum that penetrates through the ozone layer is ultraviolet. And in the process of sunlight coming from the sun, it acts to heat the Earth. Now, by having the ozone there, you protect against some of that light. Okay. However, we've been putting holes in the ozone. So what ends up happening is when there's holes, heat is actually able to penetrate through the holes, and it gets to the ice shelves, okay, which happen to be around the north and the south poles of the Earth, okay? And when heat gets there, the ice, of course, starts to melt, okay? Now this poses a problem for several reasons. Number one, excuse me, if the ice caps start to melt, what do you think that's going to do to the levels of water on the planet? Well, they're going to rise, okay? And, you know, the levels of water are going to rise, and things that are currently what you would find on land, if you continue this course of action, they're essentially going to be underwater. Okay, so the more you melt the ice caps, the more water that's released into the liquid form, the less that's actually in the solid form of water, and so the ocean levels are going to rise, and so that allows there to be less land available for people and livestock to live. And so that could potentially pose a problem in the future, since we're purported to reach about 11 billion people by the year 2100. You're going to have scarcity of foods and things like that. Resources are going to be drained, so it's a good idea to try to get this under control now before the sea levels start to rise. And what ends up happening with the ice is, in general, the ice actually acts as a coolant. So even when we didn't have holes in the ozone, when heat would come there, it would help. The ice would help to dissipate it by acting as a coolant. But the more ice that we actually lose, the less coolant ability there is. And so what happens is, because there's less coolant ability, the temperature of the planet is gradually going to rise. And particularly in the past few years, we have noticed that. That is a fact, that the temperature of the planet has risen. Okay? All of these things that we're talking about in terms of destruction of the ozone, what you're literally saying is you're looking at destruction of ozone on a molecular level. So this molecule that I showed you down here, this is the molecule that's actually getting destroyed. And there's a ton of it in the ozone layer, and it's actually getting destroyed. And certainly chlorofluorocarbons are one of the many noxious molecules that humans produce. And we're going to see through a radical mechanism that this is, in fact, how the ozone layer gets destroyed. Okay? And honestly, the reason people oppose this idea so much is because if you wanted to fix the problem, you're going to have to spend probably a lot of money, to be honest. Okay? And some people don't want to spend that kind of money. They'd rather deny it. But this is definitely, in fact, a reality, because I'm about to show you the inorganic mechanism of how this occurs. So we're about to break into some heavy-duty organic and inorganic chemistry. So if you need to review some of that, go do that. So what I'm going to start with is essentially something called a chlorofluorocarbon, which is shown right here. And this is probably the simplest one you can find. Excuse me, I have a carbon atom in the center, okay, and then surrounding it, I essentially have 4 ligands. Okay, I have one fluoro group, or a fluoride, and then I have 3 chlorides, or chloro groups. Okay, now obviously what happens is light is coming from the sun. And I could specify that this light, which I signal as HV, okay, this could essentially be UV light. I'll designate it as UV because that's the most common one that comes from our sun. And it turns out that when UV light strikes a chlorofluorocarbon, you end up generating something referred to as a radical. And the way you do it, I'll show you in green, I'll do the mechanistic steps in that color, is you get a carbon chloride bond, homolytic bond cleavage. So this bond right here, let me do this in red so you can see it. This bond right here is essentially going to undergo a homolytic bond cleavage. And remember, covalent single bonds are composed of 2 electrons. So one of these electrons is going to end up on the carbon, the other one's going to end up on the chlorine. And so what I generate is this atom right here. It's atomic chlorine. So it's not chloride. If I had chloride, there would be an extra electron right here, but there's not. So this is neutral atomic chlorine. And notice it's a radical. And radicals are extremely reactive because they have electrons that are unpaired. Okay? Now here's ozone over here, minding its own business. So what essentially the atomic chlorine can do is it can get essentially into the ozone layer on the superficial part of the stratosphere, and it will essentially do a radical attack on the ozone. So let me show you how that works. So this chlorine is essentially going to come out here, and it's essentially going to attack this oxygen. Okay? In the process, this bond right here, this bond I'm going to do in orange, this bond right here is just going to leave as a leaving group. So all that business just leaves. Okay? So this atomic chlorine essentially is going to attack the oxygen, forcing loss of the leaving group. And it turns out this leaving group, notice, it's just molecular oxygen, and there's multiple ways you can draw it. You can draw it with the double bond, or you can draw it in the singlet oxygen state. Okay? But the idea is that, once again, this is a spontaneous reaction. Okay, this just occurs by itself. You expose it to UV light and this reaction will occur. Now, if this chlorine radical attacks the oxygen, you get loss of a leaving group. That means now that the oxygen is devoid of an octet, right? Because it actually lost 2 electrons in this bond, right? And so what I end up with something called a hypochlorite radical. This is also dangerous. So I end up with a hypochlorite radical. And something else can happen because I also have something that's you don't usually think about when you're looking at gases in the atmosphere. But if I start to go into the stratosphere where the ozone layer is, I start bumping into some weird gases. Okay, so turns out there's another gas called atomic oxygen, which exists in the stratosphere. Okay, atomic oxygen is devoid of an octet, which makes it extremely reactive. And so what can end up happening is essentially what will happen is the hypochlorite radical will actually couple with the atomic oxygen. So in other words, this bond right here, let me do this in orange, this bond right here, this bond is going to do a homolytic bond cleavage. So one of these electrons ends up on the chlorine, making another chlorine radical, and then this other electron right here comes and it essentially couples with the electron on the atomic oxygen. And what that essentially does is it creates another molecular oxygen, right? And then you also get a chlorine radical. Now, this is the important point about this type of free radical chemistry. So let me go ahead and circle this again. So we get a chlorine radical. Here's the dangerous part about this, okay? What essentially was the initiator of all of this? Well, if I go back, most of these steps are just propagation steps from a radical point of view. And I guess on some level you could consider the ultraviolet light striking the chlorofluorocarbon as the initiator step, and from a mechanistic step it is. But really, in terms of the destruction of ozone, it's really this atomic chlorine that does it, right? Because this reaction of the chlorofluorocarbon doing a homolytic bond cleavage and generating atomic chlorine, that reaction is spontaneous, okay? It doesn't need any energy input to happen. It just happens automatically in the presence of light. Okay, so you use atomic chlorine to do that reaction. However, notice at the end of all of these steps, I generate another chlorine radical. So the chlorine radical actually through these reactions is conserved, unless of course it does a coupling with another chlorine, and certainly that's possible. But the idea behind ozone destruction is that it's self-propagating. Once the chlorofluorocarbon does the homolytic bond cleavage and generates atomic chlorine, throughout the mechanism, you're going to generate another chlorine radical, so it self-propagates. And so you can end up with a whole variety of all sorts of coupling products, but in the end, the chlorine radical will destroy the ozone. And so you see here this kind of step that I did. I'm showing you that the ozone, once again, it'll react to form the hypochlorite radical. Let's look at that once again. So this particular electron is going to attack the oxygen, forcing loss of a leaving group, and in that step I generate molecular oxygen and so forth, right? But the whole idea is that once you generate that chlorine radical, it's over for the ozone. So it's self-propagating, and the problem is that we keep producing molecules like this. And don't think for 1 minute that fluorocarbons are the only ones that do this. We produce all sorts of noxious molecules that end up in the stratosphere and destroying the ozone layer. This is just one example, but hopefully now you see the inorganic mechanism of how it occurs. Okay, so hopefully that makes a little bit of sense. And truly for the future of our planet, we have to really think about our kids and our grandkids. If global warming is something that continues because people don't want to pay for it, it's not really that those people directly have to pay. It's going to be their children and their children's children. You imagine that we keep melting the ice caps. For example, one of the ice caps, the Ward Hunt ice cap, a very famous ice cap that peaked about 3,000 years ago, and it was pretty stable for a long time. In 2000, about August of 2000, sometime around there, this ice cap split in half. And by 2003, it had completely fallen apart. So you can look at videos certainly online. You'll see videos of these ice caps literally falling apart. These ice shelves come apart. And ultimately what happens is you lose more and more ice, and it gets more and more water into the liquid phase. And so if there's more water in the liquid phase, over time the sea levels will rise. And you may not be able to observe it because delta T is really small, but over the course of 50 years you're going to see the levels of the ocean rise, and that poses a big problem because, like I said, the population of the Earth is purported to be about 11 billion by the year 2100. So that's probably in my lifetime. Okay, probably in your lifetime as well. So this is something we certainly have to think about, and we really have to think about spending a little money to making money, if you know what I mean. So hopefully this gave you a little bit of intuition on chlorofluorocarbons and ozone and where kind of the layers of the planet. So in other videos, we'll look at more inorganic, interesting things. See you in the next video.